Hi, everybody. We're back. It's a Thursday evening, and we're going to review Lewis structures a little bit and then talk about polarity, polar bonds, electronegativity, all this good stuff that is a big part of how molecules interact with one another. So we will wait a couple minutes, see if people join us. If you're here, say hi in the chat or on Discord in the live stream channel, which I'll be monitoring as well. And we'll have a good stream today. Hello, good evening, Daisy. All right. If everybody can hear me okay, we will get started. Okay, here we go. All right, so let's go back a little bit before we start on the new stuff. Let's take a look at drawing some more of these Lewis structures that we looked at yesterday. So I want to look here at ClO3 minus, right over here. This is 5A on, I don't actually know what page I'm on, but 5A from what we were doing last time. So let's just review that process. 6C, yeah, hey Alyssa, definitely we can do 6C as well. So we'll do that one next. So let's do 5A, ClO3. So we'll go through the typical way of doing these. We're going to count our valence electrons first. So we know chlorine has 7 valence electrons, and each oxygen has 6. And then we have to be careful because this is a -1 charge, so we've got an extra electron there. So our total electrons here are going to be 7 from the chlorine plus 3 times 6, since there's 3 oxygens, ClO3. Whoops, and then we got to remember, we can't just do that. We have to add the extra one for the -1 charge. All right, so that gives us a total of 18, 19 plus 7 is 26. So we have 26 valence electrons total to deal with in our structure. So now we start drawing things down. And before I do that, so Daisy asks, is there a certain periodic table? I mean, there's the periodic table. I don't think there are other ones, as far as I know. There's just the one, so I would use that one. If you want to send some of those links to me, or you can show me sometime what else you're looking at. Maybe some of the tables specifically list the charges, but we talked about how you get those, or the valence electrons, but we talked about how you get those also. So I don't think you'll need anything besides just the standard regular periodic table. All right, so let's go to here. We've got ClO3. So remember that these are usually done so that, okay, thanks. I'll take a look. So these are usually done so that the first, or the element that's listed first ends up being the center element. Hey, Maria. So we'll put the Cl here, and then we'll put 3 oxygens around it. And at this point, getting the structure, it doesn't really matter if you put those, up to the side or space them out evenly. When we get into the shapes, we'll look at that a little bit more. So we've used up 6 electrons. We've got 20 to go. So now we just start filling up octets. We want to make sure everything has 8 electrons around it. So we'll add 2 more to the chlorine to make sure it has 8. And then, so let's keep track of that. That's 8. And then 10, 12, 14, 16, 18, 20, 22, 24, 26. All right, so we'll look at that and let's check that one more time. We've got 26 electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So that works. Now, I would, and then because this is a negative charge, we usually always do this too. I would caution you a little bit on this. If you look this up, like if you were trying this and you weren't sure if it was right, and so you just looked up what is the Lewis structure for ClO3 minus, which is chlorate ion, you might not have found this one. You might have found one with double bonds instead. And that's because all the elements below the second row, so the third row and below, can actually have what's called an expanded octet. So they can have more than 8 electrons. So in some cases, those structures are drawn with like extra double bonds and things for reasons of minimizing something called formal charge, which we're not going to get into in this class. So for our purposes, this is a fine structure, and it's a totally fine structure for most purposes anyway. But you may sometimes find structures that have the double bond in slightly different places, and that can still be okay. All right, so let's move down to, we had a request for 6C. Okay, so yeah, this one's going to be a weird one. So what happens when you get something like NO? N has 5 electrons, O has 6 electrons, and that's 11. And we talked about last time that we can't really deal with 11 electrons. This whole Lewis thing requires electron pairs. So if we try to do this, let's see what happens. We put NO, and we put NO there, and then we've got, so that's 2 electrons, and then we got 4, 6, 8, 10. We're not even close here, so we can start making some double bonds just to try to get a little bit closer. So if we go like that, and we go like that, we could do that, but we don't have enough electrons. And anywhere we put that 11th electron exceeds the octet rule. So that doesn't work. So maybe we have to take one of those off and put it back on the nitrogen. So now nitrogen has a full octet. That's good. Oxygen's got 2, 4, 6, and needs 2 more, but we only have 1 more to go, so we have to just put it there. So this structure is an example of one that the Lewis model just doesn't work well for, because oxygen can't have an octet. It has to break the rule. And so it turns out that it's because it's kind of a special structure, and there's other ways of describing bonding in structures with odd numbers of electrons besides this. But if you encounter something like this, you just don't have a choice. You have to put something down, and you're just going to violate one of the rules. So either something's going to have less than an octet or more than an octet. But if you've got 11 electrons, you got to break one of the other rules. Okay. Any other questions on this right now? All right, we'll go ahead and put them in if you've still got them. We'll keep talking about this, but I want to move on to the next part of this, which still involves bonding and everything. And this is something called electronegativity. So instead of just kind of having a bunch of extra information here, I kind of cut all that out because we've got that in the book. So I want to pull up the book and show you that part and what you should be looking for here. So there's a chapter here, covalent bonding and electronegativity. And this kind of describes how this bonding works. So this is some of the stuff that we've already talked about. All right, so let's go down here with electronegativity. So electronegativity is a measure of the tendency of an atom to attract electrons toward itself in a covalent bond. So when 2 atoms are bonded, if those 2 atoms are different, like H and Cl or H and O or something like that, the electrons are not actually shared evenly between the 2 atoms. It's like lopsided. they get kind of pulled more to one side than the other. One picture of this is right here. So you can see this HCl bond. In the HCl atom, the electrons are actually pulled more toward the chlorine. So there's a little bit of negative charge on the chlorine, and then because they're not even, there's like not enough electron charge on the hydrogen, so that one gets a little bit positive instead. So so it's sort of this lopsided thing where the electrons go to one side and make that side more negative. And the side that the electrons get pulled to is called the ability of an electron to do that, or the measure of that, is called electronegativity. So let's take a look at a table or a measure of electronegativities. And maybe this is what you're talking about different periodic tables with different values. Get some extra space here. Oh, okay, I forgot to take the thing off here. All right, so this is in our notes now. So what you can see is the regular periodic table, but instead of all the other information that we usually see, we just have these numbers. And these numbers are measures of this quantity, electronegativity. So what we want to look for here, we don't want to memorize a bunch of numbers, and we don't want to always assume that we will have access to a table like this. So what we're going to do is think about the overall trends. So we're going to answer questions like, what is the most electronegative element? So the most electronegative element is fluorine at 4. Let me see that. Oops, it's a little bit over my head here. Okay, up there. So fluorine, electronegativity of 4. That's the highest one. And if you look at the pattern here, you can see that as you move toward fluorine in both directions, the electronegativity increases. So elements that, like as you go one away, actually throughout this first row, it pretty nicely drops by 0.5 each time. So 3.5, 3.0, 2.5, 2.0. And then as you go down this way, it drops again less evenly, but keeps going down that way too. So everything kind of trends toward fluorine, which is really handy because if all we have to do then is remember that fluorine is the most electronegative element, and then anything that is close to it, we can judge that. So if we have a CO bond, we know that's going to be polar because oxygen will have a higher electronegativity and pull those electrons toward it. Same thing with NO or SO, or H is a little bit tricky because H is actually on the periodic table way over on the left, but electronegativity wise, it's kind of more like in the middle. So that's why that's drawn this way. So just thinking about those trends, what do you think the least electronegative atom is? So even without looking this up back on that table, if we just look at our periodic table here, we can probably guess if fluorine here is the highest electronegativity, and remember we kind of ignore the noble gases over there because they don't really form these compounds much. So if fluorine has the highest, then the lowest you can probably guess is the other side. So down that way. I can't get my finger all the way over there, but over in like the bottom of the alkali metals and things like that. And if we check that on our actual table, you find that that is indeed true, that the least electronegative elements are the ones way down here. Okay, so I got a message that I got these periodic tables. All right, so yeah. So the first one you sent me is a table of electronegativities. And the second one is just valence electrons. But we should be able to get, we can get valence electrons from the standard periodic table. The electronegativities we just talked about. So we need to know the highest electronegativity, and then everything else we can judge based on how close it is to that one. All right, so let's think about that with relation to some different types of bonds. We want to predict if a bond is going to be nonpolar covalent, meaning no difference in electronegativity, no lopsidedness. we want to know if it's that or if it's polar covalent, meaning that there is that pull to one side or the other, or what we call ionic. So remember that even though we might say that these are the least electronegative down at the left, really, or down on the left, really, we don't even really think about those in terms of electronegativity because they don't really form covalent bonds in the compounds that we're looking at. They form ionic bonds because they're metals. So every is a metal anyway, and so those are going to be ionic bonds rather than covalent. So let's first pick those out. If we can find any ionic bonds here, I see one right away, right? And so really, it's not even correct to really draw that as a line because now we know that that line means two shared electrons, a covalent bond. So that's definitely ionic because sodium's a metal, fluorine's a nonmetal. So with these other ones, let's look at the ones that are obviously one or the other. So the most obvious is if it's not polar, or the most obvious way to be nonpolar is just to have two atoms that are identical. So if you have like F and F, then there's no difference between them, so the electrons aren't going to get pulled to one side or the other because there's just no difference. So the ones that are just one type of atom and both, one type bound together, like this one and this one, are definitely nonpolar, no question. You can't have a difference in electronegativity if you don't even have a difference in the atom. And this one too here. So when we look for polar covalent bonds, and you can read more about this in the book, we're looking for a difference in electronegativity between the two atoms, not just the absolute electronegativity. So yes, fluorine is the most electronegative, but the difference in electronegativity between two fluorines is 0, because it's the same thing. Okay, so now we have to deal with these more difficult ones where there's a difference. And what we can do, at least at first, until we get more comfortable with it, is look up the values on the table and figure it out. So HF, and I remember some of these. So H is 2.1 and F is 4.0. So the difference, that's a Greek letter delta, which is sometimes used to mean difference. The difference is going to be 4 minus 2.1, which is 1.9. And that's a pretty big difference. Generally, we say things are polar when the difference in electronegativity is more than 0.4. That's kind of a rule of thumb. There's not like a exact line, but generally things with a bigger difference than that act like polar bonds, and with a lower difference don't. So this one's 1.9. Cl instead of 4 is 3, so we've got 2.1 versus 3. That difference is 0.9, so that's still polar. One's polar. All right, if we jump over here to HO, H is 2.1 and O is 3.5. So that difference is 1.4, so very polar there. And then between carbon and fluorine, carbon's 2.5, fluorine's 4.0. So the difference is 1.5, polar. And then our last one here, CH, is kind of a special one. So it ends up being right on the line. Carbon is 2.5, hydrogen is 2.1. So the difference is 0.4, and that one is nonpolar. And I'm going to kind of circle that one, just because CH is such a common bond. We're going to see lots and lots of CH bonds. And it's important to recognize that those are nonpolar bonds. Because ultimately the point of doing all this is that when we think about how molecules interact with each other, we think about these interactions, and polar molecules are going to interact in one way, nonpolar in a different way. So question, do we use polar covalent ionic or just polar? So yeah, it's generally written as nonpolar covalent, polar covalent, or ionic. But because the polar and nonpolar are really we will only see them as associated with covalent bonds. So they're kind of interchangeable. Polar and nonpolar in general are more like general adjectives. Anything with two extremes is polar, like like the Earth's poles, like magnetic poles, things like that. So electrical polarity, things like that. So like in the grand scheme of life, yes, this is specifically a polar or nonpolar covalent bond. But in our class, in our purposes, we're really only going to ever use the terms polar or nonpolar in relation to covalent bonds. So it doesn't really matter for us. Okay. So the next thing we want to talk about a little bit is molecular shapes. Now, if you go on or you take more chemistry, there's way more shapes than that, but we're going to focus on just 3. And the shapes come from something called Vesper, which is spelled backwards the way it's pronounced, but it's pronounced Vesper, which basically just says that electrons repel each other, and therefore electron groups on an atom are going to want to space themselves out as much as possible. So if you only have 2 things connected to an atom, then you're going to get a linear orientation, meaning that those 2 things are going to be opposite. They're going to get as far away from each other as they can. If we have 3 things, then we have this trigonal, what we call trigonal planar. So a flat species where the 3 things are at the corners of a triangle, that's the farthest they can get away from each other. And then if we have 4 things, you'd think it might be a square or like a T or a plus sign or a cross or whatever, however you want to call that. But we actually don't want to forget about the 3rd dimension. So you can actually space these things out a little bit farther if they bend into that 3rd dimension and make this shape called tetrahedral. So a tetrahedron is a regular solid with 4 equal triangular sides, like that. And so that if the 4 groups go to the corners of the tetrahedron, that's actually how they can be spaced out the most. So those are kind of the general shapes for those types of combinations. So like we can use that and go back up to our Lewis structures here. I have to zoom out to see this a little bit, I think. So we can look at something like CO that we talked about on Tuesday and say, okay, that central carbon has 2 groups attached to it, an O and an O. And in this case, double or triple bonds still just count as one thing, one electron group. So those 2 groups are going to be as far apart as possible, which means the actual CO2 molecule is going to have a linear geometry. It's going to be stretched out in a line. The one we drew today, well, actually, let's pick a different one. Let's look at water. You may know the structure of water. You may have seen it before. But let's do it as though we're going to develop a Lewis structure and then figure out the shape. So for H2O, we've got 2 hydrogens with 1 valence electron, plus 6 for oxygen is 8 electrons total. So hydrogen can't be in the middle, so oxygen's in the middle. We put the hydrogens on either side, and now we've got 4 more electrons, which we're going to put on the oxygen here, and then everything is satisfied. The hydrogens have 2 electrons, and the oxygen has 8. Now, if we want to think about what the shape of this molecule is, we would go down to the chart here, and we'd say, all right, well, how many different groups are on the oxygen? And we can definitely see 2 groups from the hydrogens, but in terms of shape, remember we're talking about electrons taking up space. Those lone pairs actually also take up plenty of space. They actually take up a little more space than a bond. So we would really say that there are 4 groups on this oxygen, and therefore it has a tetrahedral type geometry. So if we were to draw that, or attempt to draw that, we could put the oxygen in the middle with a hydrogen up here and a hydrogen over here, and then we could imagine that one of those lone pairs is kind of in a cloud coming out at us, and another one is sort of back here, going away from us. So you have this 3-dimensional type arrangement. And there are some nicer pictures in the book, and there's videos online and stuff if you want to if you have trouble visualizing that shape. But that's that tetrahedral shape. However, we don't actually see the lone pairs, the electrons, when we actually see what the structure looks like. So it's even though they're there and they take up that space, since we don't see them, the actual molecular shape just looks like the atoms. So it just looks like this part. And so that's what the rest of this table tells us. When there are lone pairs on that central atom, rather than, because we don't see them, we get a slightly different looking shape. And like in the case of water, we're over here. So we actually have 4 groups, a tetrahedral orientation, but we only see 2 of them, so that shape ends up being called bent instead. And if we had if we had only 1 lone pair, we'd have 3 atoms, and that shape is called trigonal pyramidal. So let's do that for some structures here. So let's do H2CO. I think this one was in there earlier also, just as a plain Lewis structure. So we've got 2 from the H, plus 4 from the C, plus 6 from the O, and that gives us 12 total valence electrons. Then we can't put H in the middle, so we put our C in the middle, and we put the other ones around. Again, at this point, it doesn't matter where you put them. We need to add now 6 more electrons. If we put them all in the oxygen, there won't be enough left over for the carbon. So that tells us we need to do a double bond. And we have a structure like that. Okay, so looking at that structure now, we can answer a question like this. How many electron groups does the central atom in the above molecules have? So electron groups, remember, means bonded atoms and non-bonding pairs of electrons. So the electron groups here for H2CO, there are 3 of them. The 2 H's and the O, there's no lone pair on the carbon. So just 3 of them. No lone pairs. So now knowing that, we can figure out the shape. So we're going to use these 2 terms. Electron geometry is when we include all of the groups, including the lone pairs. So everything is the electron geometry. And for this case, that's going to be called trigonal planar. So 3 groups. We go back up to the chart. 3 groups, no lone pairs, trigonal planar. The molecular shape is also trigonal planar because there are no lone pairs for this molecule. So we just did water. So what we can, so before that then, we can kind of correct our Lewis structure. This is still a totally fine Lewis structure. But now that we know the actual geometry is trigonal planar, we might want to go back and think about kind of correcting this and drawing it in a more trigonal planar geometry like this. So we can kind of see that space. We did water, same idea. So we can draw it like this when we're making a Lewis structure. The bond angles don't matter at all when you're just making a Lewis structure. You just want to get everything in there. For water, the way we've drawn it here, we've got 4 electron groups, but 2 lone pairs. So our electron geometry then is called tetrahedral, and our molecular shape is called bent, which we get from that table. Okay. So that's mostly what we're going to do for the rest of this. We're going to extend it a little bit for bigger atoms and molecules. So one thing we're going to be looking at fairly soon in this class, rather than focus on these small molecules for a long time, is we're going to build up into bigger ones because this is chemistry for the health sciences, so we want to deal with organic compounds and biochemical compounds, you know, things that deal with the body, and those tend to be bigger molecules. So what happens when you deal with a structure like this? How do you handle that? And the answer is that you look at each individual atom and you try to just figure out what's going on based on history and based on common patterns. Now, you might not always be right because there's always exceptions. But we can use common patterns to get most of the way there and be at least mostly right and maybe totally right. So for atoms like carbon, carbon usually has 4 bonds with no lone pairs. If you look at every single structure we've drawn with a carbon atom in it, I don't know how many there are here, but there's one. Carbon, 4 bonds, no lone pairs. Carbon, 4 bonds, no lone pairs. So there are these kind of patterns that are not like laws. They're not always going to be true, but they're generally mostly true. Same thing with oxygen. Nitrogen generally makes 3 bonds with 1 lone pair. Are there exceptions? Sure, like NH4+. Hydrogen tends to have 1 bond with no lone pairs. Oxygen tends to have 2 bonds with 2 lone pairs. That's how it follows the octet rule. Now again, are there exceptions? Sure, and we've seen some of them. But especially as we get into these bigger organic molecules, they're actually going to follow the rules a little bit better. Lone pair, yes, that's a non-bonding pair of electrons. So when we say lone pair, we mean I guess I didn't write it down last time. These things. Oh, because it's here in the thing. So lone pairs that are not involved in bonding. A pair of electrons not involved in bonding is a lone pair. Thank you for asking. All right, so now, like in this big structure, it says there are 3 hydrogens and 5 lone pairs missing. Draw them in. So if we tried to figure this out, we could like look at each atom. You know, we could try to count all the electrons in the structure, all the valence electrons or something like that. It would be tedious at best. What we want to do is use these patterns to figure that out. So like this carbon has 4 bonds, no lone pairs, just like carbon likes. So we're good. We're going to leave it alone. Same with this one. 4 bonds, no lone pairs. Perfect. This one is in a little bit of a weird situation, and it should be linear. But we can say, all right, four bonds, no lone pairs. Good. We move over to this carbon, and suddenly we see 3 bonds and no lone pairs. And that tells us something's wrong. That carbon is not following the octet rule. Something's wrong there. Now, because it says we have 3 hydrogens and 5 lone pairs missing, we can either fix that by adding a hydrogen or adding a lone pair. Either one will satisfy our octet rule, but the better choice here is the hydrogen, because we know that carbon generally doesn't have a lone pair in its normal neutral state. So it's better to put a hydrogen there. And then we've got that same situation here and here also, so we can add those hydrogens as well. As for the lone pairs, they're going to go on the nitrogens and the oxygens following those same types of rules. As you'll notice, the nitrogens and oxygens here also don't have octets, so we're going to fix those octets by adding those electrons. So 2 of them here on this oxygen, 2 of them here on this oxygen, and then 1 pair on the nitrogen. So now everything has an octet. Everything is good there. So when we think about drawing some of these bigger structures with multiple atoms, especially what we are going to call organic structures where there's a lot of carbon, that's what organic structures are, rather than like if we take something like C3H6, let's not count all the valence electrons in C3H6 and then try to figure out some way to lay them out. You could, and it would still work, and you'd still get something that works, but we have a shortcut now. We're going to take all our carbons and we're going to make sure they have 4 bonds, and we're going to take all our hydrogens and make sure they only have 1 bond, sorry, and then see how we do. So let's try that. I know I can't put any of the hydrogens kind of in the middle because hydrogen generally only makes 1 bond. So the only way to really connect those 3 carbons is like this. And then I'm going to add 6 hydrogens. And then I'm going to check everything, and I recognize right away that my carbons on the outside don't have enough bonds. So that tells me this doesn't quite work. I got to add a double bond somewhere. I can't just stick it here because then this middle carbon would have too many hydrogens, but I can move the hydrogens around. So if I take one of these out, I can add a double bond here, and I can put that hydrogen over here. And I have a nice structure of C3H6. There's another perfectly correct structure or perfectly good solution to this, which is to actually close the carbons back around on themselves and make something like this. That is also C3H6, and each carbon has 4 bonds, and each hydrogen has 1 bond. So that works also. Some of these, the structure is drawn because there are lots of possibilities for how you could draw a complete structure with this, or a correct structure with this. So it kind of gets it started for you, and that means we have to follow what's here. So let's take a look at this one, E. We've got C2H3N. We have to figure out what we're going to add here to make this work. We know carbon wants 4 bonds. This carbon already has 4 bonds. This one only has 2. And we can't connect more to the left here because this carbon is already has its 4. So the only way we can get this one up to 4 is to add more bonds over here to the nitrogen. So if we add a triple bond, 3 covalent bonds between carbon and nitrogen, now we're good in terms of the carbon. Then we move over to the nitrogen, and we notice that it doesn't have an octet either. So we're going to, again, use our bonding patterns and recognize that nitrogen often has the, a lone pair. And so there it is. So finally, I want to look at sometimes where this doesn't always work. And generally, those are going to be ionic compounds, not always. But let's take a look at H here. So H, we've got CH6N3, and the whole structure is given here. So we go, oh, okay, well, let's just add some lone pairs to the nitrogens. And the nitrogens are all fine. And carbon is not. Carbon is not fine here. It only has 6 electrons. But we can't add any more atoms because this is already all drawn. So we have to kind of not break a rule, but we have to just change it up a little bit. That means that one of these has to actually be a double bond. So even though nitrogen generally is seen with 3 bonds and a lone pair, it sometimes is not, and this is one of the occasions when it is not. Part of the reason that it does that is because there's a charge here. So when you see a charged compound, sometimes that's a hint that something weird is going to happen in the structure. This one, I'll give you a hint for F. You can try that one on your own. Same kind of thing is going to happen. Something isn't going to quite work to get everything with an octet. But if we follow the octet rule, we'll be okay. So the octet rule will always take precedence over this idea of like, whoops, not that idea. This idea of the bonding predictions. Right, so you can try some of these out. And the last thing I want to talk about is that sometimes, just because sometimes a molecule has polar bonds, but the overall molecule ends up being nonpolar. So, for example, CF4, carbon tetrafluoride, we can make a Lewis structure for that. It's a fairly simple one. It's just like this. And then if we kind of sum up everything we did today, we can also look at the geometry. So we can say, how many groups does this have, and what would this actually look like? What would that shape look like? And the answer is it has 4 groups, four things attached to the carbon. So that makes for a tetrahedral structure. And if we were to draw that tetrahedral structure, it looks like this. And then often, to make it a little bit clearer, we emphasize one of the bonds to show that it's coming out at us, like coming out like toward you, like that. And then we dash one of those lines to show that one of them is going back into the board or into the screen. So one of them's coming out, one of them's coming back. The two with a regular straight line are just directly in the plane of the screen. So looking at the structure then, a carbon-fluorine bond is definitely polar. So if we are to analyze each of the bonds in this compound, we would say like let's just pick one. Let's say that bond. Let's say, is it polar or not? Well, we look at our electronegativities and we see that carbon is 2.5, and fluorine is 4.0. So that difference in electronegativity is pretty big, 1.5. So yes, that is definitely polar, a polar covalent bond. However, this overall molecule is actually not polar. And the reason for that is that all these fluorines are distributed evenly around the outside. So even though they are pulling the electron density away from the carbon, the molecule itself, the whole molecule, doesn't end up being lopsided with a positive and a negative side. It's more like the negative is on the outside and the positive is on the inside, and that's not really polar. Polar means one side positive, one side negative. So even though the bonds inside this molecule are polar, the overall molecule is nonpolar. And that really only happens with small molecules like this. When we start talking about these bigger organic structures, like these things, and we get into this more later, then we will get back to just more of the polar bonds. But some of these small molecules, you can actually say, even though they're made of polar bonds, if they have a symmetrical shape, they are nonpolar. Carbon dioxide is another example. Remember we said carbon dioxide was linear. Good question. If there are 3F, would it be nonpolar too? So let me answer that question in a couple different ways, because the answer is kind of, it depends a little bit. So carbon dioxide has CO bonds. CO bonds are polar. They have a large difference in electronegativity, about 1. But because they're symmetrical, because the electrons are being pulled as much on one side or as to the other, then those become overall nonpolar. So polar bonds, nonpolar overall molecules. So Daisy asks, if there's 3 fluorines, would it be nonpolar too? So the answer is, it depends on the molecule. So let me show you a couple examples. One where it does end up being polar, whoops, and one where it does not. So first, let's look at NF3. If we do that all out, we get this. I'm just using F because it's always, I mean, anything with F is going to be polar. The bonds themselves are going to be polar. So once again, we have 3 definitely polar bonds because there's a big difference in electronegativity between nitrogen and fluorine. So you have a definitely polar bond. And if we look at the shape of this molecule, this is also going to be kind of tetrahedral because it's got 4 groups: electron, fluorine, fluorine, fluorine. But because one of those groups is an electron, we don't really see it. So let's imagine the electron is kind of like here, and we'll put the F here, and then it's got another F here and another F like that. All right, and then I'm actually going to collapse that electron back down onto here just so we can see the shape. If we look at the shape of this molecule, what you see is that the fluorines are kind of all underneath the nitrogen. So this is making like a triangle pyramid, right, where the nitrogen is like the top point of the triangle and the fluorines are at the base of the pyramid. So in this case, since the fluorines are the things that are negative and the nitrogen's the thing that's positive in the bonds, so we kind of have this thing going on. Notice when I'm drawing these positives and negatives, I don't mean actual charges like ions. I'm just meaning like a little bit of pulling electrons. So you end up having like a nitrogen kind of top of the pyramid. Let me draw that pyramid. So let's say this is our pyramid. The nitrogen at the top is all positive, and the fluorines at the bottom of the pyramid are all negative. So that means we can kind of draw a line right in between here, and we have a positive side and a negative side. And whenever you have a positive side and a negative side, you have polarity. So that molecule is polar because it's kind of lopsided. The positives are on the top and the negatives are on the bottom. If this were flat, so if this were a molecule like, run out of room here. Let's look at carbonate ions. So carbonate ends up being trigonal planar like this. Now, because that is all flat, so rather than being like a pyramid, this is actually more like a triangle, then the oxygens being at those corners of the triangle end up canceling each other out. And so this one ends up also being nonpolar. So whenever you have like a central atom and everything around it is the same kind of atom, that tends to be nonpolar. It's only when it's lopsided in some way, and the more electronegative atoms end up on one side rather than the other, that you have a structure that ends up being polar. So this is a little bit tricky, and this is kind of like the very end thing. The most important, or the more important thing, is can you recognize the polar bonds? Can you recognize that the difference in electronegativity is what leads to the polarity? And for this exam coming up next week, I will give you the table, or you'll have access to it somehow. You'll have access to the table of electronegativities, so you won't need to remember any of that stuff. You'll have those there. Oh, thank you. Yes, my top O is wrong. I got too many electrons there. There you go. Thank you for the correction. All right. So so next week's gonna be our first exam. I'm still trying to figure out the best way to do that. I think I'm gonna end up giving people some options of how you want to take the exam. But in preparation for that, because we've just dealt with a lot of kind of new stuff, from the naming to the Lewis structures and the polarity, I'm planning next week not to have new material. So next week will be about reviewing for and studying for the exam, and we won't get into the next topic, and we'll just put that off until the next week. So when we meet on Tuesday morning, it'll be about review and practice for the exam, and then same thing Thursday evening. So answering questions and all of that to get ready. So as usual, find me on Discord if you have questions. No, there's not a separate lab exam. So lab is only the pre-labs and reports are your points for lab. The exam will only be on the stuff we've been talking about here from the handouts from the Mastering Chemistry. All right. Anything else before we go? Okay. Thanks, everybody. I will talk to you soon and see half of you on Wednesday. Good night.